All right, so we've just seen the Dedekind-Kummer theory in action. We've just done a bunch of examples of how to use it to factorize prime ideals and stuff. Now I just want to apply it to quadratic fields to completely describe what happens. But before that, I just want to prove a proposition which we may have noticed has happened in the previous examples that we did. So here's just a quick proposition which follows easily from this Dedekind-Kummer. So the K be a number field. And alpha in OK a primitive element. With the minimal polynomial, say m alpha, I want it to be Eisenstein, say at some prime p. Then this immediately tells me that there's going to be one prime which is totally ramified. So then we have the ideal generated by p is going to be some ideal frac p to the full degree of the field, with p being the ideal generated by p and alpha a prime ideal. Okay, so we saw this in the examples before. Sometimes we had x squared minus 6, which is Eisenstein at 2 and 3, and we checked that 2 and 3. We saw that 2 and 3 ended up being totally ramified. So this isn't just a coincidence. This is something that happens in general. So the proof. So first of all, if alpha is Eisenstein, if m of alpha is Eisenstein at p, then if you think of this group quotient, OK mod Z alpha, this has no element of order p. If you go back to check this by lemma 2.2.21, therefore the index, the relevant index to that we need to check so that we can apply to the Dedekind-Kummer is not divisible by p. So it's co-prime to p, say. So we can apply Dedekind-Kummer without having to worry. So we can apply Dedekind-Kummer, which was 3.5.10, which since m of alpha is Eisenstein at p gives, so the fact that it's Eisenstein gives you that m alpha of x. This is just going to be congruent to x to the degree of the minimal polynomial, which we know is the degree of the field, mod p. Remember, Eisenstein, so all the coefficients are going to be divisible by p. So when you reduce mod p, it's just going to look like something like this. So now, once you have this, then the result follows. Again, from Dedekind-Kummer. That's essentially all we're doing. Okay, so when you have nice polynomials which are Eisenstein, then you can immediately figure out some primes which are totally ramified. Okay, so let's see what Dedekind-Kummer says for quadratic extensions. So let's just think about this a little bit. So let's see what Dedekind-Kummer says for quadratic extensions. So let's do some pre-thinking about this. So if n is square free, then in q square root n, there are three possibilities for how our primes are going to decompose. Prime p, well, prime ideal, prime p So this, the fact that it's these three things, this follows from, just go back and look at 3.5.7. These are, so what's the possibility? So either the prime ideal P is going to be one of the following things. So either it's one prime ideal showing up squared, and then in this case the residue degree has to be 1, so you have this. You could have it staying prime, and then essentially you get residue degree 2, or it could split into two different ones, and in this case each of these residue degrees are going to be 1. So in quadratic fields, the polynomials can only, sorry, not the polynomials, the ideals generated by polynomials can only split into 3 different ways. And what I want to do is give you a theorem which somehow tells you how each of them splits. So what's the theorem? And the theorem is going to somehow use Legendre. Well, we'll basically boil down to some Legendre symbol calculations, and you can then use quadratic reciprocity and so on. So this is a theorem somehow relates a lot, uses a lot of tools from just a number theory course. This is theorem 3.5.17. It says following: let n be a square free integer. And I'm going to let k be q square root n and p a prime number. Then what do we have? 1, if p divides n, then the ideal generated by p is nothing but p sorry, excuse me, p in root n squared. Oh, sorry. So if your prime divides your n, then you just get one single prime squared, so you get something totally ramified. 2, if n is odd, then how does the prime, usually this is the case in a lot of things in number theory, the prime number 2 needs a special case on its own to be dealt with, and then the rest of the primes somehow fall into line. But in the prime ideal 2 is going to factor as follows. So either you're going to get 2 and 1 plus root n squared, and this is going to happen if n is congruent to 3 mod 4. Either you're going to get 2 and then you're going to get something like 1 plus root 2, sorry, not 1 plus root n over 2, and then 1 minus root n over 2. If n is congruent to a 1 mod 8, and one more line, it's just going to stay as the prime ideal 2 if n is congruent to 5 mod 8. So this is just, you'll take your prime number, and this is some congruence condition on your n will tell you how the prime 2 factors. This is what this end of this theorem is going to tell you. And then let me give these, I'm going to give these numbers, each of these lines numbers, because we'll maybe have to refer to them later. So this is line 3.6, 3.7, 3.8. I'm not sure exactly where, but I think in the proof I need to refer to these things. And the third one, which is like for general primes, so if p is odd and p doesn't divide n, because we've already taken that into account in 1, we've already taken this into account, then what do we have? We have the ideal generated by p. It's going to be the following. Either it's going to look like p comma a plus root n, p a minus root n, if you have n congruent to a squared mod p. In particular, notice that this means that n is a quadratic residue mod p. I'm just saying take the quadratic residue and that tells you the factorization. Or it's going to stay inert if n choose p. So this is the Legendre symbol if this is minus 1. This is number 3.9 and 3.10. Let me just here, this is the Legendre symbol. So in particular, once we have this Legendre symbols that we have to work in, sometimes you have to figure out what n over p is, and if your prime p is too big, you can use quadratic reciprocity to flip things over and so on. Let me just, moreover, let me just state one thing. Moreover, in 3.7 and 3.9, so in these two factorizations, this one and this one, these primes showing up are distinct. The ideals appearing are distinct. I guess I hadn't said this, but yeah, in order for this to be a proper factorization, if these two prime ideals were the same, then I just have to put a square here, and this would be ramified. But if they're distinct, then they're actually and this thing is going to be split. Okay, so I'm actually not going to prove that these two things are distinct yet. I'm going to leave that proof for a little bit later, where it'll be a little bit easier. But let me start with the proof of this theorem. So I'm going to say, let me just start for, we will defer the proof that 3.7, 3.9 have distinct ideals. I'm going to do this in 3.6.12. Otherwise, this is some corollary coming up. Or you can, because you have the notes now, you could just skip forward and have a look how you do it over there. But it would just be a bit fiddly, and might as well just wait until we have a bit more machinery to make it a little bit easier. So I won't prove this bit yet. So let's start with the first one. So for 1, we note that, what do we have? We have, if you look at what this ideal that I've given you is, which is my claimed factorization. What does this look like? Well, if you square this out, if you go back to sheet 1, we somehow played around how to factor ideals generated by 2 things, or 3 things. This is the ideal generated by p, root n, and n, which if p divides n is contained in the ideal generated by p, because if p divides n, then every element here is divisible by p, so it means that the whole ideal is divisible by, every element in this thing is divisible by p. When I say divisible, I mean divisible in the ring of integers. I mean, okay, so this root n counts. So this ideal is contained in p. So this, I'm somehow just doing double inclusion. I'm showing this is contained in this, i.e. p root n squared is contained in p. And now we're just going to do reverse the other inclusion. Conversely, if you look at this ideal, you know, p squared, p root n, and it contains the GCD of p squared and n. Right, you have these two numbers, p squared and n, the ideal generated by these two things. If you think, remember, the GCD is just some linear combination of the two things, and that linear combination will be in the ideal, so it contains whatever the GCD is. Which, because n is square free, remember n can only be divisible by p once, means it's going to be p, which is p, as n is square free. So you get the ideal generated by p, because this contains p, this is contained inside p root n squared. So we get the first one. Right, so I've done double inclusion between these two things. So for the rest of the proof of the theorem, I'm going to somehow split everything into 2 cases. And then we'll it's a bit of a mix of how to prove, but this, yeah, the steps somehow get mixed up. But I'm gonna split the rest of the proof of the whole theorem into two cases depending on the congruence mod 4 of the prime. So we will split the proof of the remaining cases into two. This isn't for part 1, I mean for the rest of the theorem. To 2 bits. The first, if n is congruent to 3 or 4, sorry, not 3 or 4, 2 or 3 mod 4. And the second, if n is congruent to 1 mod 4. Remember that when we looked at what the ring of integers was for a quadratic field, we saw that there was 2 cases, one depending on if your n was 2 or 3 mod 4, and one was if it was 1 mod 4. And so this is exactly what I'm splitting in the 2 and 3 mod 4 case. The ring of integers has a special form. It just looks like z root n, so it's a bit simpler. In 1 mod 4, it looks like 1 plus root n over 2, z 1 plus root n over 2, so it's a bit more complicated. So this is a thing. So let's start with this first one. So by theorem, this one for quadratic fields, we know that if n is 2 or 3 mod 4, then OK is z adjoint square root n. So in this case, we can use Zedekind Kummer without having to worry. Can use Zedekind Kummer, which is 3.5.10. Using, so what do you use? You use alpha to be root n, and you take m of alpha is obviously x squared minus n. So this will give number 3 and 3.6. So let me just go back. So this will give you this 3 in the case that n is 2 or 3 mod 4, and it'll give you this case, which is the only case that happens because it's 3 mod 4. So I've proven this bit and the whole of this bit in the case that n is 2 or 3 mod 4. Notice that I somehow I've split it into different settings, but this is different from this. But the these two factorizations in this case just follow from Dedekind Kummer. There's just nothing to think about. You write down the minimal polynomial. We know how to factor it in that case. So we get these two cases in this bit. So what I've not done is these two in the n equals 2 or 3 mod 4. What I mean is I need to do the other cases. So now I have to somehow redo this for the n congruent to 1 mod 4. So we need to work with n congruent to 1 mod 4. Notice that I have proven 2 and 3 in fully for when n is 2 or 3 mod 4 because these two don't apply, right? If n is 2 or 3 mod 4, then it's not 1 mod 8 or 5 mod 8. So these don't apply in the first case. So it's only the second case where this is going to show up. So let's do this. What do we know in this case? So in this case, we know the ring of integers is a bit more complicated. In this case, theorem 2.1.11 says that OK is z 1 plus root n over 2. Note that this means what does this mean? It tells us that the index of OK to z alpha is 2. Yeah, think of it as additive. You have this 2 showing up. This is essentially why this index is this kind of goes 2. But P is odd. Well, in case 3, I guess. P is odd, so but if P is odd, then it doesn't divide this index. So again, yeah, 3 taking Kumar 3.510 gives part 3. So we're left with one. Okay, so we are left with 3.7 and 3.8. So let's go back and just look at this. I've just done 3 in the case that n is congruent to 1 mod 4, and this case n is 1 mod 4, so the first case doesn't happen. So I just got to prove these 2 cases in the case that n is 1 mod 4. So if n is 1 mod 4, it could be 1 mod 8 or it could be 5 mod 8. So it's these 2 things that somehow remain for me to prove. And notice that in this case 2 does divide this index, so we have a problem. So we have to somehow think a little bit outside the box. Let me just say, note that this case, static and Kumar, so 3.5.10 won't work, won't apply. So need to think some more. So what do we do? So let's do the first one. So let's assume n is congruent to 1 mod 8, which is like the first thing, so it's case 3.7. Then what do we have? Then we have this ideal. We're talking about looking at this factorization. 2, 1 minus root n over 2. If you expand this out, what these ideals are, you get this. And you get 1 minus n over 4. So if you look at each of these numbers, they're all divisible by 2 in OK, right? Because my ring of integers is now z1 plus root n over 2. So I can divide, this divided by 2 is an element of OK, and so it's this one. So all of these elements are divisible by 2. Note, each generator term of the product is divisible by 2 in OK. So as we saw before, what this means is you get this is contained in the ideal generated by 2. And so now we just go to the reverse conclusion. Conversely, 4, 1 minus root n, 1 plus root n, 1 minus n over 4 contains the GCD of 4 and 1 minus root n. Again, this GCD works more generally in these rings, which if you think this is going to be 2, the only number that can divide this thing is 2. The only denominators that we can have in this ring of integers is 2. So GCD these 2 things is 2. So this, which gives it contains the GCD of this thing, so it tells you that 2 is contained in this ideal. Ooh. Which is the reverse inclusion. So we're almost done, so we just got to do 3.8. Oops. So finally, let's assume n is congruent to 5 mod 8. In this case, somehow we got to do even more tricks. So consider the following quotient: OK modulo the ideal generated by 2 by theorem 3.5.7. It's enough to show that this quotient is not isomorphic to Z mod 2. So what am I trying to do? Let's go back to this. I'm in the case 3.8. In here, I'm claiming that this thing stays prime. So I'm claiming that 2 is inert in this case. So what does it mean to be inert? It means that the size of the residue degree is as big as possible. In this case, it's 2. So you mean that you have a non-trivial extension of your field. So your residue field is actually a non-trivial extension of f2 or Z mod 2Z, same thing. So I just need to check that this is what my residue field, if this is a field and it's not this thing, then this is going to be it. So I'm going to say since this means the residue degree, so the residue degree is 2, and therefore, since we are in a quadratic field, it means it's inert. The prime is inert. So to show that these two things, that this and this thing are not isomorphic, let me just, in case there's any confusion, so Z mod 2Z, which I'll remind you is also called F2, the field of 2 elements. So to show they're not isomorphic, consider the following. You do the following trick. You consider the minimal polynomial of alpha in this case, which is going to be in the n equals congruent to 1 mod 4. It's going to be this. You can go back and check that this is going to be the case. So by construction, this has a root in OK, obviously, and therefore has a root in the quotient OK mod 2. So you just take your root and reduce it mod 2. On the other hand, we know that n is 5 mod 8. So if you reduce this thing mod 2, you're gonna get, so you get that m alpha of x bar. This is congruent to x squared plus x plus 1 mod 2, right? This is n is 5 mod 8, so 1 minus 5 is 4 mod 8, so this is divisible by 4. This n 1 minus n is divisible by 4, so this is a 1, and this minus 1 times 1, so we know that this polynomial looks like this, which you know is irreducible, which is irreducible in f2 of x. So, we've taken a polynomial. I've checked that it has a root in OK mod 2, but it doesn't have a root in f2, right? So it doesn't have a root in f2. So f2 and this ring can't be isomorphic. So Z mod 2 and OK mod 2 can't be isomorphic. So we're done. Okay, so let me just somehow recap what we've done. And the proof of this was a bit all over the place. The thing is that I want to have a nice statement of the theorem which looks like this, but the proof somehow doesn't break up into 3 little bits like this, or at least not neatly. You just have to go back on yourself lots of times. So the first one was if our prime p divided my n from what I'm taking square root of, then in this case this was really easy. I just told you that these two ideas were the same. I just did reverse inclusion, double inclusion. Didn't even need to use Dedek and Kummer. This was really simple. Then I split these two cases into the following two different scenarios. Either n was 2 or 3 mod 4, and prove that they're just using Dedekind-Kummer. Because the key is, once I know if I can apply Dedekind-Kummer or not, then the result is immediate. So if I can apply Dedekind-Kummer, then I can immediately figure out that this is a factorization, or that this is if it's a square or not. But if I can't apply Dedekind-Kummer, which is in the case what happens when your n is 1 mod 4, say, and your prime is 2, then you do have to, these two cases, you do have to work a bit more and just do it by hand. And again, I've not proven to you so far that these two ideals are different or these two ideals are different, but we'll do that in this corollary 3.6.12. Okay, so the last thing I just wanted to note is that you can combine this with quadratic reciprocity to quickly decompose primes in quadratic fields. So here's a remark. Using this together with quadratic reciprocity, which I remind you is, it tells you PQ over QP is -1. Oh, I got my Legendre symbol wrong, I just realized. Yeah, it's not a choose, it's a Legendre symbol. P minus 1, Q minus 1 over 4. So remember, this is what quadratic reciprocity tells you. So you can quickly use this to because most of the time your prime isn't going to be 2. So most of the time you're going to be in case 3. And case 3 is somehow determined about if it's a quadratic residue or not. Yeah, the first one I'm saying if it's a quadratic residue. I could have just put in here n over p is 1, but I somehow wanted to say that, to give the explicit description of the factorization, you somehow want to know what the quadratic residue is, what the a squared is that gives you it. But you somehow want to use quadratic reciprocity to figure this out, or so you got to figure out some Legendre symbol to do this. And if n and p are weird, or one of them is bigger than the other, then you can use quadratic reciprocity to flip them around and figure out what the Legendre symbol is. Use this with quadratic reciprocity. I'll just leave for primes P and Q. One can quickly find how primes decompose. Q10. So I want to tell you to not forget that quadratic reciprocity exists and to use it. All right. So I'll leave this here. So this is we've done all of our first applications of splitting prime ideals using this Dedekind-Kummer. Now we're going to somehow refine this, and we're going to try and do this now for cyclotomic fields. But to get there, we're going to need a lot of stuff beforehand. But yeah, I'll leave this here for now.